Inside a thick cloud bank, your sense of balance becomes your greatest liability. In a prolonged turn without a visible horizon, the fluid in your inner ear eventually stabilizes, tricking your brain into feeling level while the aircraft remains in a bank. Within minutes, a pilot trusting their instincts rather than their instruments will tighten that bank into a graveyard spiral. Whether piloting a basic trainer or a four-engine jet transport, aviators rely on the same core data to survive this sensory failure. Most cockpits organize this data into a standardized cluster of 6 primary dials, known as the six-pack. Each of these dials functions as a specialized mechanical sensor. Together, they monitor just 3 specific physical phenomena. Proficiency in instrument flight depends on understanding the behavior of atmospheric pressure, the effects of rotational inertia, and planetary magnetism. Removing the dashboard reveals the connections linking these dials into 3 groups. Airspeed, altimeter, and vertical speed indicators form the pressure-drigging pitot-static system. The attitude, heading, and turn indicators rely on spinning gyroscopic rotors. Separately, the magnetic compass reacts exclusively to Earth's magnetic field. As analog mechanical sensors, these instruments are susceptible to environmental distortions and mechanical errors. Static pressure presses equally in all directions. Forward movement adds dynamic pressure, the impact of molecules striking the leading edges. The airspeed indicator compares these. Total pressure fills a diaphragm, while static pressure fills the casing, leaving only the dynamic impact to move the needle. This dial displays your current indicated airspeed. It represents the physical force the wings feel, which determines the aircraft's aerodynamic performance and lift. However, air density decreases as an aircraft gains altitude. With fewer molecules striking the aircraft per second, the pressure readings change. Maintaining a constant indicated airspeed at high altitudes requires the aircraft to move faster through the thin air to achieve the same impact pressure. This creates 2 different speed values. Your indicated airspeed tells you if the wings will stall, while your true airspeed represents your actual velocity through the air, which is the figure used for navigation. The altimeter and vertical speed indicator ignore dynamic impact entirely, monitoring only the drops in static pressure that occur during a climb. Inside the altimeter, sealed aneroid capsules expand as ambient pressure drops, turning the gears. If ice blocks the static vent, the trapped pressure freezes the capsules, locking the altimeter at a single reading even if the aircraft continues to climb. These instruments also assume the atmosphere matches a theoretical standard temperature. When real-world temperatures vary, the calibration fails. Cold air is denser, causing pressure levels to compress toward the surface. Flying into cold air means reaching lower pressure levels at lower physical heights. The altimeter may indicate 3,000 feet, but the aircraft is physically much closer to the ground. This physical reality leads to the primary safety rule for pressure instruments. From high to low or hot to cold, look out below. Pressure instruments cannot determine spatial orientation. A pilot could be banking into a steep descent, while the altimeter and airspeed indicators show perfectly normal readings. Orientation relies on a heavy brass gyroscope spinning at high speed on multi-axis gimbals. The mass maintains rigidity in space, resisting any force that tries to tilt its axis. As the aircraft banks and pitches, the rotor remains perfectly upright. The attitude indicator uses this fixed point to show the aircraft's position against an artificial horizon. While the indicator displays movement, the internal gyroscope remains perfectly still. The aircraft rotates around the stationary rotor. Spinning masses also exhibit a secondary property called precession. When a force is applied to the edge of a spinning gyro, the resulting movement occurs 90 degrees later in the direction of rotation. This property allows the turn coordinator to translate yaw into a measurable rate of turn. As the aircraft turns, it applies a twisting force to the gyro. Precession shifts that force 90 degrees, causing the gimbal to tilt against a tension spring. This tilt moves a miniature aircraft on the dial. When aligned with the index, it indicates a standard rate turn of 3 degrees per second. This mechanical translation provides a precise readout of aerodynamic forces that the pilot cannot feel. Friction causes gyroscopic instruments to drift over time. Pilots must periodically realign their heading indicators using the magnetic compass. Magnetic field lines plunge vertically toward the Earth's surface near the poles. A compass needle follows these lines, dipping sharply toward the ground. To counter this magnetic dip, the compass card is weighted like a pendulum, using gravity to pull the card level. This pendulum mounting introduces errors during speed changes, particularly on east or west headings. When accelerating, the heavy center of gravity lags behind the pivot point due to inertia. This twist rotates the compass card, indicating a false turn toward the north. This is the Ann's rule. Accelerate north, decelerate south. Similar errors occur during turns. Centripetal force pulls the weighted card, causing the compass to lag when turning through north and lead turning through south. These mechanical flaws mean the magnetic compass only provides an accurate reading during straight, unaccelerated flight. Safe maneuvering requires the pilot to cross-reference all three systems. In an uncoordinated turn, for example, the aircraft skids outward. The attitude indicator and turn coordinator confirm the bank angle and the rate of the turn. The altimeter and vertical speed indicator verify that the aircraft is maintaining a constant altitude throughout the bank. The coordination ball reveals the skid. Excessive centripetal force pushes the ball to the outside of the turn, indicating the aircraft is out of balance. To correct this, the pilot steps on the ball by applying rudder pressure to the same side as the ball's displacement. This realigns the gravitational and centripetal forces, centering the ball. Maintaining control in the clouds requires a continuous visual scan, triangulating these three physical systems to find a reliable truth. These instruments act as analog mechanical interpreters of a chaotic atmosphere. True airmanship requires more than reading the dials. It requires understanding how temperature, inertia, and planetary magnetism can distort the data behind the glass. The cockpit operates as a system of applied pressure, inertia, and magnetism. Mastering these instruments is a matter of mastering the physics of the sky itself.